Welcome to the Explainer. So, have you ever paused during your busy day to just think about the invisible physical forces shaping our lives? We walk right through them, we breathe them in, we literally fly through the sky because of them, yet they remain completely unseen. Well, today we're going to make those invisible forces visible. We're about to decode the secret language of the physical world around us. Let's get right into it. To start us off, I want you to picture this highly relatable, maybe even slightly terrifying everyday mystery. You step into the bathroom, you turn on a nice, steaming hot shower, and just as you get comfortable, boom, the cold, wet shower curtain starts creeping inward, clinging to your leg. Like, why does your shower curtain attack you? I promise it's not ghosts, and it's definitely not a draft from an open window. The real answer actually lies in an 18th century physics formula. Way back in the 1700s, this brilliant Swiss scientist named Daniel Bernoulli discovered the invisible strings pulling that cold plastic curtain toward you. He figured out a fundamental truth about how our world works, and you know what? His discovery is still completely running the show today. Okay, let's dive into this. Section 1. What is Bernoulli's principle? The core rule of fluids. So, at its absolute core, Bernoulli's principle states that as the speed of a fluid increases, its pressure decreases. Now, when physicists say fluid, they don't just mean liquids like water. They're talking about literally anything that flows, which absolutely includes gases like the air we breathe. So basically, if water or air is moving faster, it's exerting less pressure. And this brilliantly illustrates the answer to our bathroom mystery. Think about the high contrast difference here. A fast-moving fluid equals low pressure, and a slow-moving fluid equals high pressure. When you turn on that hot shower, the steam and the air start moving really quickly across the space between you and the curtain. That fast-moving air creates a pocket of low pressure. Meanwhile, the slower-moving air outside the curtain and the rest of your bathroom stays at a higher pressure. So that higher pressure outside literally pushes the curtain inward toward the low-pressure zone, right into your leg. Moving on to Section 2, the math and energy. The law of conservation. Now, don't let the math symbols intimidate you here. We can completely understand this without being math geniuses. Looking at this equation, it really just combines three things: pressure, kinetic energy from velocity, and potential energy from gravity and height. Simply put, this principle comes directly from the conservation of mechanical energy. It means a fluid has a set, unchanging amount of energy currency as it flows. Now, what's really interesting about this slide is thinking of a fluid's energy like a donut chart made of three slices. You've got pressure energy, kinetic energy, which is just the energy of motion or speed, and potential energy, which deals with height. Because the total size of this donut literally cannot change. If the fluid spends more of its energy currency on speed, meaning that the kinetic slice gets bigger, well, the pressure slice simply must shrink to compensate. Faster speed, lower pressure. It's a perfect balancing act. Let's shift gears a bit. Section 3. Magic in the real world. Bernoulli all around us. This single mathematical constant creates absolute magic in the real world. We're talking airplanes flying through the sky, the way perfume sprays out of a bottle, the destructive force of massive tornadoes, curving sports balls, the pull of fast trucks on a highway, and even how smoke magically rises out of chimneys. Every single one of these incredible everyday phenomena is completely governed by Bernoulli's pressure differences. Take airplanes, for example. How on earth does a 400-ton airplane fly? Well, airplane wings are cleverly designed so that the top of the wing is curved and the bottom is flat. As the plane moves forward, the air has to travel a longer distance over that curved top, which means it has to move faster. And what do we know? Faster air means low pressure on top. Beneath the flat bottom, the air moves slower, creating high pressure. That high pressure underneath pushes the wing up into the low pressure zone above it. That upward force is called lift, and it's exactly what carries us safely across oceans. How about something way smaller, like an atomizer or perfume spray? Let's walk through this step by step. When you squeeze the bulb, air is forced rapidly across the top opening of a little tube. That fast-moving air drops the pressure at the top, which allows the higher atmospheric pressure at the bottom of the bottle to push the liquid up. Finally, that fast airstream catches the liquid at the top and breaks it into a fine mist. So yeah, Bernoulli is literally helping you smell great. Let's move to a different example and see how this builds. Have you ever felt a dangerous pulling effect on the highway? If you're driving when two massive trucks pass each other at high speed, the air getting squeezed between them moves super fast, creating a low pressure zone. Meanwhile, the slower air on the outside of the trucks remains at a higher pressure. This high outside pressure pushes the trucks slightly toward each other, right into that low pressure gap. It's wild.
Honestly, this principle is just everywhere. When athletes put a spin on a football or swing a cricket ball, it makes the air move faster on one side of the ball than the other. That creates low pressure that curves the ball right in midair. Or try taking a hairdryer and pointing it straight up at a ping pong ball. The fast airstream around the ball creates low pressure, and the higher room pressure traps the ball, letting it float steadily in place. You can even blow fast air between two hanging balloons, and instead of blowing them apart, the low pressure pulls them together. No way, right? But, there is also a very dangerous side to fluid dynamics. Think about tornadoes. During a violent storm, you have extremely fast wind ripping over the top of a house. This creates a massive low-pressure zone right above the roof. The air inside the house, however, is mostly still, meaning it remains at a much higher pressure. This extreme pressure difference can become so incredibly strong that the high pressure inside the house actually pushes up and can literally blow the roof right off the building. Which brings us to Section 4, Real Limits and Final Thoughts, when the magic gets messy. Now, to be fair, Bernoulli's equation relies on a few perfect, ideal conditions. The fluid must flow steadily, have absolutely no internal friction, be incompressible, and experience no energy loss. But as we all know, the real world doesn't exactly play perfectly by these rules. The real world has friction. Engineers designing airplanes and water pipes constantly have to adjust for real-world turbulence, friction, and the fact that high-speed air can actually be compressed. So the crucial point is this: even with these real-world limitations and messy variables, this 18th century principle remains an incredibly accurate approximation. It's the ultimate tool. Think of it like a cheat code for understanding fluid dynamics. It connects fluid speed, pressure, and energy to explain the massive physical mechanics shaping our world, from water pipes right up to those airplane wings. I want to leave you with this final, provocative thought. Next time the wind blows, ask yourself, what invisible forces are lifting the world around you? Once you know the rule that faster speed equals lower pressure, you'll start seeing Bernoulli's invisible strings pulling on absolutely everything. Thanks for joining me for this explainer. Stay curious and keep